All right, so let's take a look at the warm-up here. We got 4 problems. They're all improper integrals. So we want to go through these and determine whether they converge or diverge, whether we can actually integrate this stuff, whether we can actually add up infinitely many things in some cases to get a value, or if they just diverge. So we start off with the first one, integrating from 1 to infinity of x squared. And we save ourselves some time on this one. This is an important thing to look for in the exam. There are some shortcuts we can take, and this is definitely one of them. We can look at this right away and just say that it's divergent. Why is that?
Again, infinity is go up to.
What's that?
If you plug it in.
Yep.
You plug in infinity for x, go to infinity.
Sort of. I mean, that's certainly what it feels like, right? And that's kind of how you can think about it. The only thing I hesitate on is I don't like to plug in infinity because it's not a number value we can plug in. But you're exactly right. What we're looking at x squared and saying what happens when this thing gets big? What happens when this goes to infinity? Our integrand is getting bigger and bigger and bigger and bigger. The height of all those rectangles that we're adding up is getting bigger and bigger and bigger. So if we're adding up infinitely many things and they're getting bigger as we go, there's no way that will have a finite value. And so there's no way this could be convergent. So it absolutely diverges. So we can just write that one off right away. That one's done. Now we start on the next one, and I have my work up here. That first step is to say, okay, I'm not sure what's going on here. If I looked at a plot of this actually is getting smaller, because this is getting smaller much faster than this is getting bigger. So our integrand here really is going to 0. But that doesn't mean it necessarily converges. That means we have to test it to find out whether it does converge or whether it doesn't. Okay? So it's definitely something we have to investigate. So we get rid of the problem spot. We replace the infinity with an a, and we express it as a limit. So we're rewriting our improper integral as the limit of a proper integral. Any questions about that? And then I actually have to do this integration. And so that's a whole other process, right? In this case, I look at the integral, and I see that I have an inside function up here, negative x squared, whose derivative looks something like x. So that tells me substitution is the right technique. So I let u equal negative x squared. I take the derivative, solve it for dx. I'm going through those substitution steps here. Plug everything in. My x's cancel out. I'm really just integrating. To pull out my negative 1/2, I'm really just integrating e to the u. The integral of e to the u is e to the u. And then I replace the u by what it's equal to, negative x squared. So that's kind of my antiderivative right here. And I'm evaluating that from 0 to a. I keep carrying my negative 1/2 limit kind of along as I go. I evaluate it at a and at 0. And now I have to actually apply that limit. So far this is just kind of mechanical, just doing a regular integration where we have a letter instead of a number in our limits of integration. But now comes the part where we have to see if this thing really converges or not. What happens to this term as a goes to infinity? Goes to 0. Remember, this is e to the negative a squared, so that's the same thing as 1 over e to the a squared. So this thing is going to 0. And then what's the limit as a goes to infinity of negative 1? It's negative 1, right? It's just a constant value, doesn't change. There is no a in that piece. So I really just get negative 1/2 times negative 1 or positive 1/2. So this integral from 0 to infinity is 1/2. Yep?
Exactly does it mean that something converges? Does that just mean that it crosses the x-axis?
No, converges. So we talk about series converges, and then we talk about maybe an integral. It might not be the technical word to say that the integral converges. What I mean, I guess, would be that the limit of that sum converges. So I guess the way I'm kind of probably misusing it here is saying that we can actually find this integral value, that it will have some finite value, we can calculate it, as opposed to it being divergent, which means we can't calculate that value. We have a value for it. Yep. So if we talk about series, which we'll do later in this course, we'll talk about adding up things that look like this: 1 plus 1/2 plus 1/4 plus 1, let me change this a little bit here, 1/4 plus 1/9 plus 1/16 plus ... going to infinity. And the question is, can we add up infinitely many things? Kind of like the question we're having now. And it turns out sometimes we can, sometimes we can't. And so as we add up these things, if I would draw a picture of their sums, like if I would take this thing, 1, and plot 1 has a height of 1, and then add a little more, go up a little higher, add a little more, go up a little higher, and if I kept doing that over and over and over again, my values would be getting closer and closer to some value. They would be converging to that number. That's what I should be saying with convergence. Good question. Other questions? Okay, so for the next one, but this thing looks good at 4, this thing looks good at 10. Is this thing even improper? It is improper because there's a problem at x equals 8. Somewhere inside of that interval from 4 to 10, our integrand is blowing up. It's getting really big. So we have to kind of investigate it there. So really what I'd like to do is rewrite this as the integral from 4 to 8, 1 over x minus 8, plus the integral from 8 to 10, 1 over x minus 8, like that. And that's one of my properties of integration, so I know I can do that. But 8 is my problem point. So actually, to kind of save time, I'm only going to work with one of these integrals. In general, we have to treat both of them. But as we talked about yesterday, if one of them blows up, I just stop right there. So I'm just going to work on this one right here. I'm going to really look at this as the limit as a goes to 8 of the integral from 4 to a. Not infinity, 8. There we go. And I have to work on the integral. I could do a substitution on this one, or I could almost guess and check this one. So I look at that, and I know it to be the natural log of x minus 8. And I could check that with taking the derivative. You have to be a little bit careful there. Like if this was 2x minus 8, you'd have to account for that factor. If I take the derivative of this, I would get 1 over x minus 8 times the derivative of the inside function. But in this case, the derivative of the inside function is just 1. Okay, but if there was a 2x, or if this is 8 minus x, would there be a minus sign from the x? I'd have to be a little more careful. But that's my antiderivative evaluated from 4 to a, which means I'd be taking the limit as a goes to 8 from the natural log of a minus 8 minus the natural log of 4 minus 8. Now I'm going to say this thing is divergent, but I want to be very careful here. Why is it divergent? Why does the value for this definite integral not exist? Yep. Absolutely, because as we get, I keep writing infinity here for my limit instead of 8. Right? As a approaches 8, as I get closer and closer and closer to a equal 8, a is never actually going to equal 8, but as I get closer and closer to a value here of 8, this is getting closer and closer to 0, which means this, the natural log of something getting closer to 0, is going to be getting closer and closer, not closer and closer to negative infinity, but it's going to get bigger and bigger and bigger in the absolute value, right? It's going towards negative infinity here. Okay? So that's a problem. That's why this diverges. I'm stressing to be careful here because so often on an exam, I get students who do this part wonderfully. They write the limit, they do the integration, boom, they get this. And they say, oh, natural log of a negative number, you can't do that. Well, that's why it's important to carry that absolute value sign. This term is just fine. It's the natural log of the absolute value of negative 4, which is natural log of 4. That's some number value. Okay. So I have people do all this wonderful work, say something about the negative, and they don't get credit for that final piece here. Right, this was divergent because this piece is going to negative infinity. Yep?
If we were doing one of these problems, we ended up with something in parentheses that looked like 0, ln, the absolute value of 0. So ln of 0 you can't do, but because there's a 0 in front of it, it's still DNE, or...
Good question, right? That would be a little tricky. The question is, how do I evaluate that limit? The limit as a goes to 0 of a natural log of a, one's getting big, one's getting small. How do I handle that piece? That's an excellent question. It's a question we run into in this next problem here. So anticipating the questions, excellent. Any questions about this one, though?
Yeah, where'd the 8 10 go?
I dropped it,
Okay.
right? I should do that next. I should do both of these. But if one of them is divergent, the whole thing is done, right? So I can just kind of stop there. So I just kind of didn't do that piece to save time and space. But absolutely, I would have to do both. Like if I got some number value 4 here, I would have to go back and look at this to see if that gave me a number value or not. Okay?
But if you run into something on the example like this, you don't have to do both.
If you show that one of them is divergent, if you say the whole thing is divergent, I'm perfectly fine with that. Okay? Other questions? Okay, so I'm going to shortcut this next one as well. We've done that integral a couple times by integration by parts, but we have kind of seen the result. So I'm going to look at this as the limit as a goes to 0 of the antiderivative here is x natural log of x minus x. That's what that antiderivative is if we did it by integration by parts, evaluated from a to 1. So this is the limit as a goes to 0 of a natural log of a minus 1 natural log of 1 minus 1. That piece is 0. The limit of this piece will just be positive 1. The limit of this piece is just 0. So really the question is, what's the limit as a goes to 0 of a natural log of a? And this is a tricky one because I don't necessarily know how to evaluate that limit. Now in application, there's lots of ways you can kind of investigate this. Right? Plug in some changing values of a. Plug in a equals 1, a equals 0.1, a equals 0.001, 0.00001. You can kind of investigate it like that. That is by no means a proof, and certain magical functions can defy that, right? But it's a nice way for normal functions to take a look. You could also maybe plot that and kind of see what's going on here as we go closer to 0. Now, to formally figure out what that limit is, we're going to use a trick called L'Hopital's rule. So I want to just mention this real quick. L'Hopital's rule. L'Hopital's rule is a technique for finding limits. Technique for finding indefinite limits. So it's something that some Calc 1 courses is covered, some unfortunately it's not. So we use it under certain circumstances. If we're looking at a limit where I have the ratio of functions, and if I look at the limit, there's a competition between 0 and infinity. I'm in the case where, this thing's going to 0 and this thing's going to 0, which is like this thing's trying to make it small and this thing's trying to make it big. So I don't know what's going to win. Or they're both going to infinity if I look at the individual pieces. In this case, it's making it big. In this case, it's making it small. I'm having this battle between big and little. And if I'm in that situation where I have a function here that has this battle between big and little, there's a trick. There's a theorem that says the limit of this function is going to be the same thing as the limit of this function, where I just take the derivatives of these two functions. And sometimes taking those derivatives will simplify the function so that I can actually take the limit. Okay? So when we're looking at a case where we're trying to take the limit of something, some ratio of functions, and the limit of the individual pieces is 0 over 0 or infinity over infinity, that tells me I can use this rule. And instead of taking the limit of this thing, I'll take the limit of the derivatives and see if I can take that limit. And the last little note there is if I try to take that limit of the derivatives and it doesn't exist, L'Hopital's rule no longer applies. It doesn't tell me anything about the original thing. It only works if I can take that limit. So this hopefully will make more sense if I do an example here. Here are two examples. The first one, sine of x over x. I think our immediate thought is probably, doesn't that thing blow up? Aren't I dividing it by 0 as I get closer to 0? But the problem is, even though the denominator is going to 0, the numerator is also going to 0. They're both going to 0. So the numerator is trying to make this thing small, the denominator is trying to make this thing big. I don't know what's going to win. But I am in that form where the limit of sine goes to 0, the limit of x, as x goes to 0, goes to 0. So I'm in that 0 over 0 form. So now I can apply L'Hopital's rule. L'Hopital's rule tells me this limit is the same as this limit. The limit of, well, the derivative of sine is cosine, and the derivative of x is 1. So instead of taking the limit of the ratio of functions, I'm taking the limit of the ratio of the derivatives of the functions. I can only do this because it had that starting form, though. And I'm happy with that, because now this is just the limit as x goes to 0 of cosine. And what is the limit as x goes to 0 of cosine? 1. Right? Cosine curve looks like this. As x goes to 0, cosine goes to 1. So it really simplifies things. The next case, yep.
So you're saying sine of x is going, as x approaches 0, is going to 0, and the x is going to 0. So both top and bottom are getting smaller and smaller?
Yep.
Okay.
And so there's a competition here. As the numerator goes to 0, it wants to make this fraction go to 0. It wants this fraction to get smaller. But as the denominator goes to 0, it wants to make this fraction bigger. So it's going to win, right? I mean, if I had the limit as x goes to 0 of this thing, oh, I see that's infinity. Right? But if I had the limit of x goes to 0 x, it would be 0. So it's that battle case that I'm in here. All right, the next one. The limit as x goes to infinity of natural log of x over x. Well, as x goes to infinity, the natural log goes to infinity. So it wants to make this fraction bigger. But as x goes to infinity, the denominator, it makes the denominator go to infinity, which wants to make this fraction smaller. So I'm in the infinity over infinity case here. That's the form I have. So it matches that form, so I can use L'Hopital's rule. So instead of taking this limit, I just take the limit of the derivatives. The derivative of natural log is 1 over x, and the derivative of x is 1. So this is really the limit as x goes to infinity of 1 over x, which is what? Zero. As x goes to infinity, 1 over x goes to 0. Now, how does this apply to our problem up here? Here I'm trying to find the limit of a times natural log of a. I don't even have a fraction here. And I don't know what this form means. But the trick here is I can rewrite this like this. And this is kind of obnoxious. Right? Because if I wanted to simplify this, what would I do? I'd just flip and multiply, right? So dividing by a fraction, I'd multiply by the reciprocal, which would get me to this thing. So these are the same. But in this form, I say what happens as a goes to 0? As a goes to 0, this thing goes to infinity in magnitude, goes to negative infinity. What happens to this thing as a goes to 0? Also infinity. So now I'm in an infinity and an infinity case. So now I know I can use L'Hopital's rule. Instead of evaluating that limit, I evaluate the limit of the derivatives. The derivative of natural log of a is 1 over a. 1 over a is really like a to the negative 1 power. And so if I take the derivative of that, I would get negative a to the negative 2 power, or negative 1 over a squared. I'll flip and multiply. I'll get 1 over a times negative a squared. So it looks like I'm looking for the limit as a goes to 0 of negative a. And what is that limit? What's the limit of negative a as a goes to 0? What's this limit here? Yep. Let's use a values to get closer to 0. When a is 0.1, this is negative 0.1. When a is negative 0.00001, this is negative 0.00001. As a gets closer and closer to 0, a gets closer and closer to 0. Okay? So I can evaluate this limit to be 0, and now it turns out my integral has a value of 0 plus 1 or 1. Okay? All right, so L'Hopital's rule is an important piece of Calculus 1, and it's an important technique for finding limits. Often it's not covered in Calc 1, so we didn't want to present it here. I won't have any integrals on the exam that are going to require you to use L'Hopital's rule. Yep?
Is there like a pattern that would be like wise for us to look for here in like the first term? Because for two of these examples, or I don't know how many of these examples, as you take the limit of the term with the a in it, it goes to 0. So do we like almost always want that term to go to 0?
We always want that term to go to 0. Right. Not necessarily. I'm sure we can find other examples where the limit of that term is going to be 2 or 4 or some finite number. But the bottom line is either it goes to a finite number or it goes to infinity. So it's either converging to some specific value or the integral is divergent. And that's really what we're determining. So it's common for things to go to 0. If you prove a lot of limits, a lot of times it's algebra to turn it into something like 1 over a so that we can show it goes to 0. So. Yep, unfortunately, there's no magic trick for these improper integrals. You have to go through the process. You definitely can't make the mistake of looking at the form right away and saying, oh, this thing is going to be convergent because this thing goes to 0. You can't just assume that. Okay, a lot of time our intuition gets messed up when we're talking about infinity. So if you have this improper case, unless that integrand doesn't go to 0, in which case you can just say it's divergent, but every other case, you have to go through the process. Rewrite the integrals, limit of a proper integral, do the integration, and then simplify, find the limit. All right. Any questions? Okay. All right, like I said, what I'd really like to do now is just pass out the keys to that practice exam that I sent everyone. I'd like you to get into some small groups here and just hopefully everybody's started that practice exam or worked through that practice exam a little bit. I'm sure there are some who haven't. I want you to compare what you've been getting to what you see on here. See if you have questions. Try to help each other out in your groups. See what you come up with. Group has questions. Feel free to raise your hand. I'll come over and work on some stuff together. If you have other questions not related to this, feel free to ask me as I'm walking around. Somebody get one here? Everybody get a key? KB key already? No. Okay, so everybody should have a key, correct? Okay. So the area under a function is the integral of the function from a to b, and the area between two functions is the integral of the difference of the functions. So we have arc length. So arc length formula. So we did the derivation, quizzed you on the derivation just to really hammer that thing home, because it's hard to memorize this stuff, so if you can kind of remind yourself of where it comes from, that's important. But if I have some sort of function, maybe it's sine of x, and maybe this is pi, and I want to find this distance, It's just the integral from 0 to pi, those are a range of my x values, 1 plus the derivative of sine, which is cosine, squared, the derivative squared, dx. Those integrals tend to be hard, so you'll probably have to evaluate those with a calculator or something, but that's how we set up that integral. From there we talked about the volumes of rotation. So I'm giving you 3 formulas here, but you have to understand they look very differently if we're rotating this thing about the y-axis. So you need to understand kind of where these things are coming from. The first one is a disk. If we were rotating the yellow region, this region right here, if we were rotating this about the x-axis, there would be no gaps in the middle. There would be no holes in the middle. So it would be the disk technique. And so it's pi r squared, because if we cut a slice and we draw the other side of it and cut that slice is just a solid disk. This is the radius. My function value is the radius. So pi function squared is the area of this circle. The dx is for the thickness, and then I add them all up. Now if I wanted to take the blue region and rotate it about that x-axis, I would have a gap in the middle, so I'd have to use the washer technique. So the washer technique just says take a big volume and subtract out the hole in the middle. And if we just do a little algebra, we get to this formula. It's pi times big radius squared minus little radius squared. So here my big radius is just to this thing. In this case, my f of x is 1 maybe, or whatever number this is, minus my little radius, which whatever that function is, sine of x, I guess. Yep. It's not so much you need to derive those formulas. I just think it's very important to be able to take any general idea. Like, so all this is saying, I have some volume, I don't know how to find it, I'm going to cut a slice. What does my slice look like? It looks like a washer. This is how I find the volume of a washer. Right? So it's not that you have to derive them, but depending on what problems, or when you get to real life, the hard part of real life is getting the model and turning it into an integral. Right? In real life, it's like, well, I want to find this total cost for my company. That's a really big problem. Well, maybe I can find the total cost that we've accumulated in one day, right? And then do some sort of integration process to find the total cost over a year. So it's that idea of little problem integrating to make it the total answer that's important. Okay? Okay. And then the other thing we can do is the shell technique. Now this way the shell technique is written to do a revolution about the y-axis. You can certainly do a shell technique to find this rotation as well. You just have to solve for the function in terms of the other distance and do some other things. So the way we've written it here is for a rotation with the y-axis. Now what this says is, here is one of my shells. I'm rotating it like this now. All right. And this formula just says you take my radius, which is this distance, that's x. So 2 pi r, it says radius 2 pi is the circumference. That's my circumference piece. And the thickness piece times the height. So those 3 dimensions give us the volume of this shell. We add up all those shells. So this one would be for this region rotated about the y-axis. Okay. Questions about that at all? So we could really set up these up specifically to this function even, because that's sine of x, and I have a height of 1. So for this blue region rotated about this axis, it would be the integral from 0 to pi, I'm using a range of x values here, 2 pi times x times 1 minus sine of x dx. I can really get that value here. If I wanted to find the volume rotated about the x-axis using the washer technique, it would really be the integral from 0 to pi of pi times big radius squared minus little radius squared dx. That's the blue region about the x-axis. The yellow region, so the yellow region about the x-axis would just be a to b, or 0 to pi, of pi times sine squared x dx. Okay? Now that's just kind of the basic application. You need to practice taking that and going about the other axes too. When we talked about surface area was a topic. How do I take this curve? I can make a volume by or an object by taking this curve and rotating that about an axis. And I want to find the surface area of this bowl. And to do that, I have a formula. And so the formula is basically taking the arc length, this looks like that arc length piece, looks like a little piece of the arc length, little piece of the arc length, and taking that thing and rotating it around some circle. So 2 pi f of x, that f of x is the height of the function, that's essentially the radius of the circle I'm rotating my arc length around. So this is a circumference piece, I have an arc length piece, and I want those pieces to make sense like that. Okay? So for this one, it would be the integral from 0 to pi of 2 pi sine of x, the square root of 1 plus cosine squared x dx. I could really just write that piece out. Okay. After that, we got into Chapter 7, integration techniques. Integration by substitution, the main points. It's a process that reverses the chain rule. We use it when we can identify an inside function whose derivative is a factor. So here I have an inside function whose derivative looks something like x. X is the factor. If we had more time, we'd work through these. When we talk about integration by parts, it's a process that reverses the product rule, and we have a formula for it. We use it when this integral on the right-hand side is easier than the integral on the left-hand side. And the real trick here is to identify u and identify dv, and then we find du, and then we calculate v, and we plug it in and go through the process. Next, we talked about partial fractions. We're just using an algebraic technique to simplify things. So here I have kind of a weird example. Remember, for us to use this technique, the degree of the polynomial on the bottom has to be bigger than the degree of the polynomial on the top. If we have a cubic down here, we need to have something smaller up here, a quadratic or a linear term. If we don't, we have to use polynomial long division to simplify that. And then we write out our forms, we solve for the coefficients, and we do the integration. Now in that process, we might get things that look like this, which we need trig substitution to do. Or we might run into other things that have square roots of quadratics in general, quadratics, and we use trig substitution. Remember, trig substitution was a technique to take a squared minus x squared and just turn it into one trig thing squared using our Pythag theorem. And that's what we have here, trig substitution. When we have the root of a quadratic or some other quadratic that's giving us problems, we can turn those pieces into just one trig thing squared. All right, that was a big, long problem we're going to go through. We're not going to have time to do that. So that's really all I got for class today. All right, the exam is in class tomorrow. There's going to be a policy change for the exam, though. So the last thing here, I'll send an email about this as well. I'm going to make one change to the policy. I am going to let you use a 3x5 note card for the exam. So you can use a handwritten 3x5 note card, front and back if you want. You are allowed to use that for the exam. And I'll email that out as well.
Are you going to be in your office?
Yep, should be there 12:30 today. Yep.